All right, so I think we'll get started. Welcome to the first Star Talk of the year featuring Professor Gwendolyn Eadie. If more people trickle in as the talk starts, that's totally fine. So for a few introductions, Dr. Eadie is an assistant professor jointly appointed between U of T's David A. Dunlap Department of Astronomy and Astrophysics and the Department of Statistical Sciences. She is an expert in astrostatistics and is currently applying modern statistical methods to the study of the Milky Way. So without further ado, take it away, Professor Eadie.
Thanks for the nice introduction, and thank you so much for inviting me. So this is a talk that parts of it I have given before, but part of it is new. So you guys are seeing it for the first time. I've tried to compile all the things that my research group are working on. So you're going to see things that my graduate students are working on in both statistics and the astronomy department. So because I'm in astronomy and statistics, I thought a fun title would be Statistics Meets Astronomy, Challenges in Time and Space. And that's because the work I'm doing is, it really is spanning both the time domain and spatial domains as well. So one place I'd like to start is just appreciating this photograph. So this is an image taken in California by photographer Ian Norman. And it's a long exposure of someone sitting in this park and looking up at the sky at the Milky Way Galaxy. And the long exposure is what enables us to see, all the dust lanes and all the stars and everything. Of course, it never looks like this to the naked eye. But I love looking at these kind of photos because it reminds me of our position in the Milky Way Galaxy, and that we actually have like a strange perspective on the whole universe because of our position. So where are we in space, and where are we in our galaxy? Or in other words, like, what is our perspective, right? Because in space, there's no up and down or left or right. So we know we're on the planet Earth, right? This is a famous image taken by the Apollo 17 crew. And the Earth is orbiting around the sun, and the sun is in the disk of the Milky Way Galaxy. And so what's important to remember is that the plane of the solar system isn't aligned with the plane of the galaxy. So here's a nice animation created by the American Museum of Natural History. And as we zoom out here, you can see these are the paths of the different planets, right? And they all kind of make roughly a plane of our solar system with the sun at the center. And we can extend this plane further out from the solar system to see how it's oriented with respect to the Milky Way's plane. So as we go out further here, you're going to see they're going to extend this grid further and further so we can keep our perspective. So all we can see now is the sun. We're thousands of light years out. Now we're starting to see stars in the neighborhood of our sun, what's called the solar neighborhood. And you can see there's the plane of our solar system. And we are sitting just outside one of the spiral arms of the Milky Way Galaxy. As you can see, we're actually at a really large tilt. The plane of our solar system is almost perpendicular to the plane of the galaxy. And so I think it's good to keep this perspective when you think about when we look out in the universe and study things, that we actually have this interesting spatial perspective. So a more static view of that is if we were to look at the Milky Way from above, you'd see that we're just outside one of the spiral arms. We're about 8 kiloparsecs from the center of the Milky Way. And if we were to look at the Milky Way from the side, it would look like a disk with a bulge. And the sun is within that disk, but it's again, not at the center. And for a sense of scale, the diameter of the Milky Way is about 100,000 light years across. So it takes light 100,000 years to go from one side of the Milky Way to the other. Oh, yeah, there is someone in the waiting room. Thank you. Okay, I just let them in. So as I go through this talk, I just want you to remember that we observe the universe from this perspective of ours in the Milky Way. And this is a perspective in both space and time. In space, because we're oriented in this interesting orientation, but also in time because the Earth is turning. And so as we're turning, we're looking around at different parts of the galaxy and different parts of the universe. Okay. So first I'm going to talk about challenging spaces. And I've taken 2 of the projects that I currently helping with. One is about the mass of the Milky Way Galaxy, and the other one is about other galaxies in the universe. So first I will talk about the Milky Way. This is something I've actually been working on since my PhD. I've been asking the question, what is the mass of the Milky Way Galaxy? And you might wonder, well, why do we even care about the mass of the Milky Way? Well, the universe is full of galaxies of all sorts of different types and sizes. And by looking out in the universe and looking at the positions of all these galaxies, what we've discovered is that there's actually kind of a hierarchical structure. And that's what's shown in this next slide here. So this is actually a figure from real data. And the way to think about this figure is that we are sitting at the very center of this. And every point in this figure represents a galaxy. And so as you go from the center out to the edge of the circle, you're looking further and further into space. And so as you can see, the galaxies tend to cluster into sort of these, almost like these strings of galaxies, or they cluster into groups. And we see this structure throughout the universe. The areas of the diagram that are just blank, we just haven't looked in that area, right? So this is a case where, right, we don't have complete data here. We haven't looked everywhere with the Sloan Digital Sky Survey, but where we have looked, we definitely see this hierarchical structure. And to recreate this hierarchical structure in computer simulations of how the universe evolved, we've discovered that you have to include something called dark matter. And so astronomers think there's like this dark matter particle that is a subatomic particle of some kind. We don't know what it is yet. No one's detected it directly. If they did, they'd probably win the Nobel Prize. But we need to put these dark matter particles in the simulation to create enough mass to sort of collapse in on itself under gravity. And then those places where the dark matter is concentrated, as you see in the simulations, that's where galaxies can form. And so it's thought that every galaxy in the universe, including the Milky Way, is sitting inside of this massive dark matter halo that we can't see, but that is made up of dark matter particles, and that actually represents a really large portion of the mass of the galaxy. And so this is one reason I'm interested in estimating the mass of the Milky Way, because if you can estimate the total mass, then you can subtract out the matter that we can see and figure out how much dark matter is there, and that might tell us something about the nature of dark matter itself. So how can we estimate the mass of the Milky Way? Well, one way is to use what's called kinematic tracers. So let's go back to our cartoon of the Milky Way. And a common kinematic tracer are these things called globular clusters. And these are star clusters. And here's a real picture of one taken by the Hubble Space Telescope. It's shown on the right here. And the Milky Way has about 150, almost 160 globular clusters. And they're orbiting around the Milky Way, and we can measure how far away they are from the center and how fast they're going. And then if we assume something about the gravitational pull from the Milky Way, which is related to the mass, then we can infer how much mass is within their orbits. And so this is what it means to use these kinematic tracers. But remember, we have to keep into account that we have this weird perspective in the Milky Way, right? We have what we call a heliocentric perspective, which just means, helio here means the sun, because we're sun-centered. Oh yeah, there's no one else in the waiting room. Thank you for reminding me though. Keep reminding me, please, because I'll forget to check. So when we look out at a globular cluster, right, we're measuring its velocity components, right? So it's a three-dimensional velocity. So you can measure it in different directions. We're measuring that from our reference frame from the Earth, right, from our sun-centered system. But the models for the galaxy that we want to test, those are all written mathematically in like a galactocentric frame. So where the center of the galaxy is what's important. So when we take these measurements, we have to transform them from our observations to what they would be measured at from the center of the galaxy. So that's one challenge. Another one is that we don't always have all of the data, right? So measuring these velocity components is difficult, and we usually split them up into two components. One that is sort of on the plane of the sky, so it can have different angles to it, and the other one is along our line of sight. So there's a line of sight velocity, and then the one on the plane of the sky is called the proper motion. And for some objects, we have both of those measurements, and so we're all good. But for some of them, we're missing the proper motion, and for others, we're missing the line of sight velocity. So we don't even have complete velocity information for those objects, and that makes it challenging. Another thing is that our measurements are not perfect, right? There's always measurement error, and that has to be taken into account because that's going to make our mass estimate even more uncertain if our measurements are uncertain. If we don't take those into account, then we could be overconfident in our results. Another assumption that is often made about when people use these kinematic tracers is what kind of orbits they have. Because when they're going around the Milky Way, their orbits take a really, really long time. They could take millions of years. And we are not around that long, so we have to kind of infer what their orbits look like. And so we might not be sure if the orbits tend to be more like elliptical in shape, or if they tend to be more circular in shape, or if there's some mixture of different types of orbits. And people try to sort of write this down mathematically and then estimate this parameter called velocity anisotropy, which tells you like what, on average, what kind of orbits does the population of kinematic tracers have. And finally, interpretation is a challenge too, because lots of people have estimated the mass of the Milky Way, but they report those mass estimates at different distances from the galactic center. And that's what I'm showing in this plot on the right. So along the horizontal axis here, we have the distance from the center of the Milky Way, measured in this weird units called kiloparsecs. And then on the vertical axis, this is the mass within that radius, measured in 10 to the 12 solar masses. And we use this unit called solar masses, which is the mass of the sun, just because mass is so big that measuring it in kilograms would sort of be really, really hard to comprehend. Even this alone is hard to comprehend. This is a 10 with 12 zeros after it. So I don't know about you, but I have trouble thinking about what that means. But what you can see here are all these points with error bars are mass estimates from other studies, and they're reported at all these different distances. And say at 100 kiloparsecs, some of the mass estimates agree with each other, but some of them don't, right? So this interpretation of the mass of the Milky Way is quite difficult. Okay. So what I've been doing with my research is developing what's called a hierarchical Bayesian method. So Bayesian statistics, or Bayesian inference, is a way of using probability and probability theory to infer estimates for model parameters given data. So imagine you think that the dark matter halo of the Milky Way follows some mathematical formula, but you need to figure out what some of the parameters are in that formula. Then you could use this method to figure out what estimates of those parameters were, and you do it in a probabilistic way. Okay. And what's advantageous about this hierarchical Bayesian method is that it allows us to include the measurement uncertainty. It allows us to incorporate this incomplete data that I talked about. We can estimate what kind of orbits the objects have. And in the end, we get an estimate of the mass of the Milky Way and an estimate of its mass profile, which I'll show next. Oh, sorry, not next. In a minute. So yeah, there's no one in the waiting room. Thank you for reminding me. All right, so we're going to use it. We're going to use this hierarchical Bayesian method. You might ask, like, what is the data we're using? And we're using data from something called the Gaia satellite, which was it's a satellite at L2, I believe. So it's out in space, and it's measuring the positions and velocities of over 2 billion stars in the Milky Way Galaxy. And it had one of its major data releases back in 2018. So this data is completely open to the public. If you wanted to go use it, you could go to their website and download their data and like query it and play with that data. But just to give you a sense of how large this data set is, this is a figure created by the Gaia collaboration from that data. And I say a figure because it's not a picture. Every single point in this figure is a star. So they've actually plotted the position of all of the stars that Gaia measured and created this figure. And when they do that, then they can actually see, the plane of the Milky Way, and all of these dust lanes and everything show up not because they've measured the dust lanes, but because they haven't measured any stars there, because the light doesn't go through the dust. So I just think that that's a really amazing figure that the Guy team put together. And with this data came velocity measurements as well for many of these stars and for all of these globular clusters that are going around the Milky Way. So we went and used these globular clusters to estimate the mass of the Milky Way with the hierarchical Bayesian method that I talked about. And this is the result that we got. So this is the same kind of plot I was showing before, where we have distance from the center of the galaxy outwards, and then on the horizontal axis. And then on the vertical axis, you have the mass contained within that distance. All the points with error bars, those are mass estimates from other studies. And then the gray bands, the shaded bands, those are our mass estimates. So these gray shaded bands are what I meant when I said the mass profile. Because now with these bands, we can read off what the mass is within any distance from the center of the galaxy, and then get an uncertainty in that mass estimate right away. So we were hoping that this, doing this kind of analysis could help improve our interpretation and start to help us understand where some studies are agreeing with each other and others are not. Okay, so the next thing I've been doing is using dwarf galaxies. So dwarf galaxies they're really faint and very small galaxies, so much smaller than the Milky Way. There's many different types of dwarf galaxies. They can actually have spiral arms too. They could be irregular shapes. They could be ellipticals. But the main point is that they're a lot smaller, and they tend to orbit around other larger galaxies. So the Milky Way has about 30 of them orbiting around it. And this image here, taken by the European Southern Observatory, shows the small and large Magellanic Clouds, which are two of the dwarf galaxies going around the Milky Way. And I haven't seen them myself. You have to be in the Southern Hemisphere to see them. I've been in the Southern Hemisphere, but I don't think I was ever in dark enough skies to be able to see it. Okay, so with these dwarf galaxies, they can also be used to measure the mass of the Milky Way because just like the globular clusters, they're in orbit around the Milky Way, right? So if we can get their positions and velocities and then use a model for the gravitational potential, then we can infer how much mass is there. So here's an animation, and it's just showing how these dwarf galaxies might be orbiting around the Milky Way. And the Milky Way is very small in the center here, but remember that the visible part of the Milky Way is actually sitting within this massive dark matter halo. So these dwarf galaxies are actually probing that dark matter halo even more than the globular clusters were, because the globular clusters were more centered around the Milky Way. All right. So this is another way to show you how much further out the dwarf galaxies go. Here I'm showing the 3 different velocity components for the globular clusters and for the dwarf galaxies. So we have distance from the galactic center along the horizontal axis, and then the vertical axis in each panel is just one of the velocity components. So remember, there's 3 velocity components in total. One is the line of sight. One is the line of sight velocity, and then the other 2 represent that 2D vector of the proper motion. So the triangles are the globular clusters, and you can see they really live in the closer to the Milky Way, and all the black dots are the dwarf galaxies, which go much, much further out. So they're really going to help us get a mass estimate that and includes more of the dark matter halo. So I've been working with an undergraduate at the University of Washington, Annika Slazewski, and then 2 undergraduates here at the University of Toronto, Xander Dufresne and Keslin Murdoch. Keslin just graduated, but he's still going to be working with me this summer, and Xander is also working with me this summer. And then Robin Sanderson is a assistant professor at the University of Pennsylvania, and Andrew Wetzel is a assistant professor at UC Davis, and then Mario Jurek is at the University of Washington. So one fun thing about academia is sometimes you'll end up collaborating with people all over, which is kind of neat. So with this new data, we've been able to get a new mass estimate for the Milky Way, and this is this is our new mass estimate, or new mass profile estimate, with those bands where we can get a estimate of the uncertainty in our mass. And we're finding that with the dwarf galaxies, we actually get a much larger mass estimate than we were before. And we're currently trying to figure out exactly why that is, and also why some of these dwarf galaxies seem to play a large role in determining what the mass is. So the mass estimate might change when we take some of the dwarf galaxies out. Okay, so that was all about the mass of the Milky Way. The next thing that has to do with challenging spaces are what other galaxies are in our local universe. So if we zoom out even more, here again we have the Milky Way in the center, and then all of its dwarf galaxies are clustered around it there. If you go out even further, our biggest neighboring galaxy is Andromeda, or M31. It also has its own population of dwarf galaxies. And this is all just part of what's called the local group. And beyond that, there's other groups of galaxies, there's other clusters of galaxies in the universe. And these galaxies that come in all shapes and sizes. They're spiral galaxies, dwarf galaxies, ellipticals, irregulars. But what was recently discovered, like I think in the early 2000s or so, was a new type of galaxy. And these are called ultradiffuse galaxies. Okay, and they're called ultradiffuse because they're like these wisps of galaxies that are very hard to detect. Here's an inset of an ultra-diffuse galaxy on the right, and it's been like blown up to scale. So it's to scale next to the Andromeda galaxy, which is our biggest neighboring galaxy. And this might help explain why they're called ultra-diffuse, right? So it's almost as big as the Andromeda galaxy, but you can see it doesn't have like a central bulge to it. There's no strong structure. It's just kind of a vague semblance of stars in there. And when people look at these, we know that they're really faint, and they have this very low surface brightness, which means there's not very much light per area on the image, and that's what makes them so difficult to detect and why we didn't detect them for a long time. So they're difficult to find with standard telescopes, but we would like to find more of them because we have found some, and we're trying to understand how these ultra-diffuse galaxies form. They're sort of unexpected. We don't understand how they fit into the scenario of galaxy evolution in general. But to find them is tricky because we can't find them with standard telescopes. You need like a space telescope like Hubble to really image it. But getting telescope time for things like Hubble is very competitive, and when you write a proposal to try and get telescope time with Hubble, you have to tell it where to look. So, how do you write a proposal for Hubble time if you don't know where to point the telescope to say, look for an ultra-diffuse galaxy here? It would be pointless to just kind of point it everywhere and hope that you get one. So we really want to be able to find more of these. Another reason is because they appear to have a ton of dark matter, and some of them appear to have very little dark matter. So these are really interesting objects. We need to find more of them so that we can understand them as a population. So one thing that I'm going to be working on with a new PhD student that's coming into the statistics department this fall is we're going to be looking for a new way to discover these ultra-diffuse galaxies with spatial statistics. And we can do this because it's been shown that some of these ultra-diffuse galaxies have objects around them, and they may be clustered in some way. And these objects around them that are clustered in some way, those objects we might be able to see those in ground-based telescope data. And so maybe if we can do some sort of spatial statistics to identify where things are clustering, then we can say, okay, there's a high probability that there's an ultra-diffuse galaxy there. Please give us some Hubble time and let us use the Hubble Space Telescope to image that part of the sky. And then we can hopefully discover ultra-diffuse galaxies. So this is work I'll be doing with David Lee, who's an incoming PhD student, and then Robert Abraham, who's the leader of the Dragonfly Telescope at Toronto with his collaborators at Yale, and then Associate Professor Patrick Brown, who's he's a statistician in the stats department, and he also is at the Center for Global Health Research. And he's a specialist in spatial statistics. Okay, so those were the two challenging spaces that I talked about. And so next we're going to go on to timely challenges. So here's 3 questions, and it's okay if you don't know what these words mean right away. I'm going to go through them one at a time. So the first one is fast radio bursts. So fast radio bursts are these brief pulses of at radio wavelengths that people first detected in about 2007, and they have this unique feature. So on the right here, this is sort of a funny plot to think about, but it's time along the horizontal axis and then frequency along the vertical axis. And so what this is showing us is that there's an increase, there's an intense signal that comes in at first at high frequency, and then it continues to come through, but the frequency of that signal tends to go down over time. And this sort of swooping signature in these kinds of diagrams is indicative of these fast radio bursts. And most of these fast radio bursts appear to be coming from outside of our galaxy. And basically, we have no idea what is causing them. Like, we have some theories, but it's a pretty open question because these fast radio bursts were just discovered, and we don't really know where they're coming from. There was one in just this past summer that was discovered within the Milky Way, though, and it was associated with a magnetar. So that was pretty exciting. The other interesting thing about these FRBs is that some of them actually burst repeatedly. So it's not just that they have one burst, but they have a bunch. And this has been discovered in large part because of this Canada-led project called the Canadian Hydrogen Intensity Mapping Experiment. So this is a radio telescope in Penticton, British Columbia, and it's called CHIME for short. And this CHIME telescope has detected a lot of repeating fast radio bursts. So we're starting to get a large sample of these types of objects, and we'd like to understand, what are there patterns in how they repeat? Are there patterns in how strongly they go off and how much they repeat? All those kinds of things. But one thing about CHIME is that it's a transit telescope. So a transit telescope is stuck to the Earth. We can't point it in any direction. So if you imagine with this video, if we were the transit telescope, we're stuck looking in a certain direction, and we only see the sky that's passing overhead, right? So as the night goes on, if we want to look at a certain portion of the sky, that portion of the sky will only be going through our field of view for about 15 minutes per night. So this creates like a statistical problem, because in nature, maybe you have a fast radio burst that's repeating in time in some way. So all these little bursts are supposed to represent that fast radio burst going, and then time is moving to the right. But the data are what we call censored, right? Because CHIME doesn't look at everything all of the time. So if CHIME were to look at this one particular fast radio burst that's at a certain point of the sky, it would only look at it in certain observing windows. So when the telescope is actually looking at that correct portion of the sky, everything else it would just miss those bursts. So with this censoring, it's going to affect how we interpret how this fast radio burst is repeating. So what a PhD student in the astronomy department and a postdoc are working with me to try and understand what kind of biases can occur when we so we're trying to figure out what kind of biases can occur because of this censoring of the data. So if we want to try to estimate some parameters for a model for repeating fast radio bursts, then we have to take this censoring into account. So what Amanda is doing is she's simulating like mock FRBs, and then she's observing them with the cadence of CHIME. So by simulating data, you know what the true repeating pattern looks like, and then you censor it, and then you run your analysis as if you didn't know what the truth was, and then you can investigate what kind of biases could occur. Okay, so that's the fast radio burst. The next one is how often do pulsars glitch? So pulsars, if you haven't heard of them before, they're rapidly rotating neutron stars, and they're very highly magnetized, and they have these beams of radiation that are emitting radiation out from the poles. And because they're rotating very rapidly, these beams tend to be tilted from their axis of spin. So you can get these beams are spinning around almost like a lighthouse. So these are like astronomical lighthouses. And if the beam is crossing with Earth, then we can detect that lighthouse kind of signal from it. And these lighthouse signals have been thought to be very precise clocks, because if you observe them for, say a day or something, this lighthouse beam that you detect every time it points at the Earth is arriving at a very regular time. And they're spinning so rapidly that it's like on the order of milliseconds or seconds. So you get a lot of these rotations in even like a 20-minute observation. But what people have discovered is that over the long term, pulsars can have these glitches. So what these glitches are a sudden increase in the spin frequency. So it's like the pulsar is spinning at a certain rate, and then all of a sudden it starts to spin way faster. And so that's what this glitch is. And it starts to spin way faster, and then it will decay back down to its original spin frequency. And it's thought that this happens because of something with the superfluid and the crust of the pulsar. But people think we're observing these glitches in the data. So what we're doing for this project is we're trying to study the statistical properties of these glitches. And the issue with the data that we have is that it's also censored in time, just like the FRB data. We have data from the Jodrell Bank telescope, which is in the UK, and it can't look at all the pulsars all the time. So not only are we only looking at a certain amount of times, but those observing windows aren't even like regularly spaced. They're kind of at random times, they're at different lengths. And so it's possible that we could miss glitches, right, that have happened. And these glitches can tell us about the interior of the pulsar. So if we've missed a glitch, we might misinterpret the physical characteristics of the pulsar. So we need to account for the fact that we might have missed some of these glitches. And that's what this PhD student, Daisy Ebick, is working on along with postdoc James McKee at the Dunlap Institute. And so she has data from 2 pulsars measured by Jodrell Bank. And she's done some analysis on those to try to estimate when the glitches have happened. And now she's using a state-dependent Poisson process model, which just means like, when glitches happen could depend on when other glitches happen. So she's using that to try to understand how often the glitches happen. And then she's also going to be simulating mock data to then investigate how the censoring could affect our estimate of these parameters. Okay, so the last one is how do red giant stars evolve over time? So to talk about red giant stars, I first have to talk about our sun. So our sun is a medium to low mass star. And here's a real image of our sun on the left, and then very much a toy model of the sun on the right, just to show us the interior. So the interior, we think that the sun is, we're quite sure that the sun is in hydrostatic equilibrium, right? So there's this radiative pressure outwards from the fusion in the core, creating radiation. And then you also have the gravitational forces trying to collapse the star inwards. And these things are in balance with one another. So this is why we say it's in hydrostatic equilibrium. And not only that, but there's a bunch of different layers to the sun. So at the center, there's the core, then there's this part called the radiative zone, and then outside of that, there's this area called the convection zone where material is actually sort of bubbling up to the surface, and then as it cools, it falls back down. So people often describe this as like a pot of oatmeal boiling on the stove, right? So you have these convection cells. And then outside of that, there's the photosphere and the chromosphere. But because there's this region of the convection zone and material is moving around, and sort of, you can think of it like bumping into the layers below it, you can actually end up with sound waves inside of the sun. So these are called like pressure modes, and there's also gravity modes, but I'm just going to talk about pressure modes here. So these are literally like sound waves inside of the sun. And if you look at the sun over time and measure its brightness on the surface over time, you'll get what's called like time series data. And with that time series data, you can look for small fluctuations in the brightness, and those fluctuations will be periodic, due to these sound waves that are inside of our star. And so people do this by looking in what's called the frequency domain. So they'll take this time series and then transform it into the frequency domain to look at sort of, are there signals for these periodic components. So here is an example of a power spectrum for the sun. So the way you can think about this is it's along the horizontal axis is frequency. And so if there is a sound wave inside the sun that is you know, oscillating at a certain period, and if that signal is strong, then you would get a peak at the frequency at which it's oscillating in this power spectrum. And so all of these peaks that you see in like this envelope actually tell us about the interior of the sun, because they're related to the mass and the radius of the sun and the density of the material. So people measure like the distance between these peaks and the heights of the peaks. And then that can actually tell us about the mass and the radius of the sun itself. And this can be extended to red giant stars. So here's to scale the sun on the left. And then the biggest star on the right is the largest red giant star that was measured by the Kepler spacecraft. So it's not actually an image, but they've taken an image of the sun and made it red and, you know, expanded it to be the appropriate relative size to the sun on the left. So these red giant stars have really large convective envelopes. So they have a lot of material that's sort of going to the surface and falling back down. And so what people want to know is like, how common are these types of oscillations in red giant stars? And can we identify different evolutionary stages for red giant stars? Also, if we can learn about the material that the star is made of, then that could tell us about the convection zone itself and how deep it is. We could learn about internal rotation. There's all sorts of questions you could ask. And so to do this, you need to look at a star, the red giant star's brightness over time, and then look at that thing called this power spectrum. But it's made a lot more difficult because these red giant stars are so far away, they're like points of light. And so the time series data isn't as good. It's also missing a lot of points because, again, the telescope can't look at all the stars at all the same time. So you have gaps in your time series data, and there's different ways to deal with this statistically. And I'm not going to go over all of it, but some recent work that I've been doing with some statisticians is to compare this kind of a standard method that's been used in astronomy called the Lomsgargle periodogram. So that's the top one here. And you can see that it kind of shows where those oscillations are in this power spectrum. And we've introduced this new method called the multi-taper Lomsgargle, and you can see that it brings out those solar oscillation modes a lot better. Hopefully because we're dealing with the uneven sampling of the data in hopefully a better way. Okay, so the other good thing about this method is that with these time series data for red giant stars, if you have these, if you figure out what frequencies the star is oscillating at, and you know the mass and the radius of the star, then that can actually tell you something about the age of the red giant star. And so this brings me to my PhD student's project, where she's looking at red giant stars within star clusters in the Milky Way. So she has data from the Kepler spacecraft, which is the time series data, and she's using that to get age estimates. And then she also has spectral data of the stars. So this is my student Arya Patel. She's co-supervised by Associate Professor Joe Bovey. And we've also been working with Sebastian Jahamel. Sorry, I think I misspelled his name here. He's a professor in the Department of Statistics. And so what we've been doing is using a new method to analyze these spectra. So spectra of stars, you know, you can look at a star and split up the light from that star, and then look for lines in the spectrum, like emission lines or absorption lines. And those will tell you what kind of chemicals are in the star, like what the star is made of. Is it mostly hydrogen? Does it have some carbon in there? Does it have magnesium? Because these things will tell you about the evolution of the star as well. The issue with this data is that we have hundreds of thousands of spectra from the Sloan Digital Sky Survey. And then we also have all the time series from Kepler. So what Ari's been doing is using new methods from statistics to try to deal with analyzing all of these data more efficiently and robustly, so in a way that's reliable. So she's using something called likelihood-free inference to estimate the chemical composition of these stars, and to fit the spectra, she's using something called functional principal component analysis, which Sebastian is an expert in. And then she's using our time series analysis, the multi-taper alarm struggle, to try and get these age estimates. So the figure I'm showing here, the black points, those are the actual data from the spectra. So you're looking at the different wavelengths along the bottom, and then it's just sort of the flux or the strength of the signal on the vertical axis. And the yellow line going through the points is the fit from this functional principal component analysis. So we're really encouraged by this. It looks like it's doing quite well, and it's pretty fast. So we're hopeful we can use this for all of the stars going forward. And for the likelihood-free inference, she's getting probability sort of distributions for these parameters that we're interested in. So this almost goes back to the Bayesian thing I talked about in the beginning, where if you take a probabilistic approach, then you can estimate, you can get an estimate of the parameters and the uncertainties in those parameters relatively easily. So in this plot, she's just plotting all the different sort of chemical components in this particular star versus one another to see what their relationships are. So those are all the timely challenges, and I hope that you know, you have developed an appreciation for these challenges that we have with these large data sets in both space and in time. And I think it's important to remember when we're looking at all these kinds of things in astronomy that we do observe the universe from our telescope's perspective in space and time, and we have to take those things into account. We have to understand our observational process and account for it properly, because only then can we overcome these data challenges, big or small, and discover things about the universe. So I think I will leave it there, but maybe I'll just show this one last slide. So this is that Gaia figure showing where all the stars are that were measured by the Gaia satellite. And I'm going to take the picture that was taken in California and show you how that is oriented in this image. So I'll just leave that there. So that's sort of our perspective from Milky Way. Okay, thanks. Are there any questions? Okay. I am at 1 hour. If people want to type a question in the chat. Everyone is muted, so. Oh, thank you. Thank you so much. Yeah, thanks again for inviting me.
So once again, thank you to Dr. Eadie, and just as a reminder to everyone else, if you're interested in watching this talk again, it will be posted on our website. So feel free to check that out in a few days if you'd like to revisit anything that's covered.
Great, thank you everybody.
Wait, Professor Eadie, you do have a question. It just appeared in the chat box if you'd like to.
Oh, yeah, I see. Why did the more massive stars get more reddish in the simulations? Oh, are you asking about this one? Is this the slide? Ah, okay. Oh yeah. So these ones aren't simulations. This is just like an artist's impression to kind of give you an idea of what a red giant star looks like, relative size to the sun. So if the sun were as big as the small dot on the left here, then a red giant star could be as big as the one on the right here. It's shown as being more red because red giant stars actually are more red in color. So stars shine at they'll shine at a bunch of different wavelengths of light. Like our sun, it looks yellow to us, right? Yellowish or maybe white, but it's actually giving off radiation at a whole bunch of different wavelengths. And we can sort of say what color a star is by looking at what does it predominantly give out light in. So with red giant stars, they're just giving out more red light than blue light, and so that's why they appear more red to us. I hope that answers your question. Hey, you're welcome. Okay, well, if there's no more questions, thanks again for inviting me. And I hope everyone is doing well.
No worries. I think since you're the host, you have to end the talk, but
Okay, I will do that.
Perfect. All right. Have a good day.
Thanks. Bye.